speaker is Chris France from Alta Devices. And you're going to hear all about these wonderful solar panels these guys make. They're actually making them here in, are you guys in Menlo Park or Sunnyvale? The factory is very impressive. I did not know that you guys were making or growing the solar panels here in California. I thought they were expensive before, but then when I found out that they were being made here, I'm like, man, this is a bargain. Anyway, would you please welcome Chris France. And here's your clicker. And there's a laser on there. Don't shut it out the window.
Okay. Yeah, there we go. Good morning, everybody. Thank you much for time and attention today. Patrick, thanks for having us, and thanks for the good introduction. Alta Devices has been around since 2007. We've been here a couple of years, so you might have heard us speak before. Patrick's a little taller than me. So we're going to talk today about harnessing the power of the sun to extend your UAV's performance. And we think the best thing you can use for that is Alta Devices gallium arsenide solar. So going to just start with a brief overview of how solar energy works, a Solar Energy 101 course, and then talk a little more specifically about solar for UAVs and our Any-Light technology. And then we're going to close up with a couple quick case studies where we have proven that Alta Solar gives dramatic improvements in range for a wide variety of small UAVs. So, Solar Energy 101. So a solar cell technically is called a photovoltaic, and I like that word because it tells you exactly what it does. You take a photon of light and you turn it into electricity. So these are semiconductor devices, similar to what's on a lot of roofs around here, right? And the material properties are going to determine how the solar performs and in what cases. It's going to determine the amount of light it absorbs, the voltage produced by the cell, and the energy lost if you're operating in a high temperature regime, and how sensitive it can be to moisture, UV, radiation, and other parameters. And one of the key things is only certain technologies allow you to become thin, flexible, and lightweight. And I would think most people in the room would agree that that's pretty important for the UAVs. And the key parameter out of that is the band gap of the solar material. And what you end up having is this trade-off. Certain material, you can absorb a lot of light, but the power you get out is at a lower voltage. And then other materials, you get, in a high band gap material, you get less of the solar light, but you get more power per electron that comes out. And all the fancy theory that has come in shows us that the theoretical limit is right here, and gallium arsenide's band gap is right around the best material you can get for optimized solar performance at the surface of the Earth. It also is also near the optimum as well once you're at high altitude for UAVs as well. And the overview, in the solar field, you've got a wide variety of materials. If you've got solar on your roof or you drive by a large solar farm, you're kind of looking in this regime, the copper, indium, gallium diselenide, cadmium telluride, and your silicon. Your calculators and other things that are often used indoors tend to use low efficiency material. And then gallium arsenide exists up at the record setting for single junction, and this is the technology gives us an advantage of a high energy density from a weight standpoint and from being able to capture the most amount of energy per your area. And your UAV applications require a handful of constraints, and flexibility is, of course, important because you've got most of your wing surface is not perfectly flat, and that rules out a lot of technology. You also need the high efficiency due to the fact you have a very limited area to generate your power, and even on top of that, you need a lightweight material. And when you factor all those in, there's really only one solution that is viable to really give you the best gains possible, and it's gallium arsenide. When also looking at solar, it's important to understand kind of what sort of energies we have available to us. The benchmark in the solar industry is 1,000 watts per meter squared. Now that is approximately the amount of energy you're going to get at high noon at a latitude approximately like where we are here in California on a good summer day. In the wintertime, that's going to drop down. In the mornings and the evenings, as the light goes through more atmosphere, that also drops lower. Some of those conditions being you're in about 600 to 1,000 if it's sunny and clear, drops down to about 300 to 600 in partially cloudy, and if you're in San Francisco 9 months out of the year, you're probably at the 100 to 300 range. And in UAVs, you have a lot of, so this energy is, in UAVs, you have a lot of different constraints that you don't have to worry about in a lot of other solar, including the fact that the solar plane is always moving, and as it changes orientation, you're going to get a slightly different amount of power. Planning your mission from talking to some customers can be important. If you're doing a mapping mission and you map in one direction, whether north-south versus east-west, could change the amount of solar you get over that day. Also, you want as much solar directly facing the sun as possible. If you've got a certain profile where you're going to be moving, certain planes can be optimized to kind of have their wing surfaces pointing towards the sun, and those are things to think about. And then as you go to higher altitudes, where there's less atmosphere, you also get a boost in the amount of power. So your high-altitude UAVs tend to get a little more solar irradiation than most of the small UASs. And one thing you also have to consider when dealing with this is that shading from the plane can limit the amount of power. So if you've got a large tail and that tail produces a shadow over the solar, it could shut down part of the solar. So you want to make sure when you design these things, you want to minimize those impacts. And on a little more, so in solar for UAVs, we want to see kind of the gallium arsenide has been this benchmark material. It's been heavily adopted in the satellite industry. Almost, pretty much all solar in space is a multi-junction gallium arsenide-based solar material. Multi-junction thick crystal gallium arsenide is heavy, but it is robust to the moisture, it's highest efficiency technology, and a really great temperature coefficient. And so when you find that as you get away from your laboratory conditions, gallium arsenide will often perform even better than other technologies than on their data sheets. And it is ideal band gap. The biggest issue is the cost. The cost of gallium arsenide wafers traditionally is very, very expensive. The wafer alone is approximately 200 times more expensive than a silicon wafer per area. That cost is mostly driven, it is slightly more expensive inherently, but it is often driven by scale. The first solar cell materials in the silicon market were scrap wafer materials that were not good enough to be turned into microprocessors, but still good enough to make solar. So that allowed the silicon industry to have abundant material and start down a path of lowering cost. And the other application, the limitation is its rigidity and heavy weight. And there's a lot of numbers behind this. This is an NREL efficiency chart. This is updated 1 to 2 times a year as the National Renewable Energy Lab in Colorado updates and tests new solar material. And the record efficiencies, this is date across the bottom, I'm sorry it got cut off, and the efficiency of the solar that they've tested. These are your record 4-junction cells, very, very expensive and complicated to make. Triple junction is slightly behind, and dual junction, and more practically, for any intent purposes, almost all the solar on this chart besides this is all single junction. And the single junction records top out here, and our technology at Alta Devices is right there. So we are the record holder in the single junction efficiency. We also have done some dual junction work, and that record has slipped away slightly, but we'll see what happens. So if you need the energy density and you need flexibility, this is really all you're going to find. Our goal is to take this technology and bring it to a broad market. And to do that, we know we have to increase the volume and decrease the cost. We have a great plan and a great technology for this and have put lots of effort into it. And the key is to design our own tools. We have a designed custom MOCVD reactor with a focus on solar, a focus on volume, and a focus on efficiency. So these reactors use less of the precursor material, keeping costs down, and have the highest throughput in the world. We have a technique known as epitaxial liftoff that allows us to grow the solar film and then remove it from the expensive substrate. That allows us to reuse the wafer. And a thin film has enabled a technology that's called photon recycling, which actually allows us to have that record efficiency over a thick film, gallium arsenide film. And then our process has been designed to have a flexible product size so that it can fit on a small UAS, a large UAS, work in the sensor market, or do any place that you need solar. So no matter what your size is, we can probably cover it in solar relatively efficiently. So I wanted to talk a little about photon recycling. This is an interesting phenomenon that we didn't even actually know about when we started, and we were trying to explain why we were getting even better efficiencies than we thought. And we realized it came down to the fact that if you make it thin, your solar material, you may have to make your solar material thin, and you have to make it very high quality so that there aren't any defects to lose the energy that you've collected. When you do that, your solar cell actually works like a really good light emitter, which is an interesting fact, and it traps the light into the solar material so that if it re-emits that light, it then gets reabsorbed, and that's why we call it photon recycling. So the better our solar cell works as an LED, the better it is as a solar cell, which is an interesting, was something our development team found interesting. And then so the next things we need to think about is as far as what do we have to worry about when we're designing the solar into the UAV or into whatever the customer's product is. And for those constraints, we have to look at how we can get the voltage into your battery system. And so we end up doing that by connecting in series and parallel. As you add the matrices in series, you build up to the voltage that your system needs or your power electronics, and then you stitch the matrices in parallel to collect as much current as possible. There's diodes that are required to protect against leakage and shading, especially if you have a UAV that intends to run in dark conditions. If the solar's not working, traditionally the battery would drain into the power, into the panels when they're off. And that needs to be designed in to make sure you got a robust solution. And then there's a little bit of electronics required. So this space over the last year, these are DC-DC converters that optimize the operating point of the solar so that you're getting the most amount of energy no matter what light condition you're in. It's vital to get the most power, and in the last 4 years, this space has really, really increased with a lot of major companies providing these solutions. So that's been the biggest improvement I think that's helped us when dealing with customers over the last 5 years, is that the technology that supports the solar has really increased. And the really nice thing that UAVs don't have to worry about the storage in some ways other products do is the fact the best way of storing the electricity for when it's shady or when you need the extra power for a climb or anything of that sort is the batteries that if you're an electrically powered UAV, you already have. So in general, we're taking our solar, finding the right power management chip to get the energy into your batteries and power your systems, and then match your solar panel voltage to that. Once you have a plan for how to electrically connect solar, you also need to worry about how is this going to be physically integrated into your craft. So you need to think about flexibility and weight, and often once you get to a thin film solar solution like our Anylight technology, most of your weight is actually in the encapsulant material that you put in to protect the solar. So not only do you need a thin solar cell, you need to make sure that you're getting away from metal and glass substrates, or metal or glass or very thick polymer laminates in the protection or encapsulation of the material. So the encapsulation requirements drive a lot of things. It's going to drive the product lifetimes. The thicker material you put in is going to allow less moisture to come in, but at the same time may also attenuate some light. And traditionally in solar, we're talking rooftop, we're looking for about a 25-year lifetime. So that requires a very robust encapsulation, no matter what technology you're using. Indoor appliances, 2 years, it's a lot simpler. And in the UAV sphere, because this is definitely a very cutting edge and an always evolving market, this standard has not really been set. Most of the customers we talk to are kind of rating the lifetime of their craft in the number of landings rather than time. And as we move forward, we know this is a place where we're going to want to work with our customers to figure out what is exactly needed. If you're looking at a short lifetime, you can get away with a very, very thin and lightweight material. Now, independent of what solar you're using, you can usually do that. But some materials are going to be a lot more moisture sensitive. Your other thin films tend to be CIGS, CadTel, or an organic. Those all are moisture sensitive. Gallium arsenide is not. So we can get away with a very, very thin front sheet. You can survive the elements, it works well, and minimize your weight. And then, of course, the key last thing as far as material considerations is you want to fill the solar wing with the wing with as much solar as possible. Also in layouts, and a point I forgot to put on this slide is that you also have many options for putting the solar on the wing. We have customers who have used adhesives. We have customers who have laid up the solar in the manufacturing process of their wings. So actually embedded in the composite carbon fiber or fiberglass, so that it's a robust solution and permanent to the plane. And speaking of some of those customers, these are 2 case studies I would like to highlight to close out, in that we have shown dramatic 2 to 4x increases in endurance on several chassis. So one is the AeroVironment Puma, which is a pretty big mainstay in forward reconnaissance in the military. These are hand-launched, robust, simple to use in the field, and provide very needed surveillance for the soldiers that are using them. So this UAS is about 160 watts of our thin film gallium arsenide fit on the wing. This plane had about a 2 to 3 hour endurance before being connected to solar, and has demonstrated repeatedly over 8-hour flight times with the solar on it. So when you think of that as far as what type of mission, either in a military or a commercial environment, that enables, by going from 2 hours to 8 hours, you've opened up a lot of doors. The amount of craft that you have to fly to survey an area, the range and the time that you can loiter, or the range and time that distance you can travel, is dramatically increased. We've been working in the last year, and this is kind of a little outdated as far as the names. We were working with a customer going as aerial vista. They now use a plane called the Cyclops C that is a composite several meter wing plane, and this is actually shown here. This is sold by Asia Tech Drones, but they were developing this chassis for working on an anti-poaching challenge over in Africa, the Wildlife Conservation UAV Challenge. And we've provided 60 watts of thin film gallium arsenide, and this craft went from a 6-hour endurance up to a 10-hour endurance on our first integration. There's a couple improvements that we think we can make to this, and we think this craft could fly under the right lighting conditions for 12 hours plus. So, and this example is not actually, the solar UAS we were hoping would be here, but it's actually not with solar, but there's an example of the Cyclops in the booth next to us. So come find us over in the corner. It is a big red 3-meter UAV. You're not going to be able to miss it. But it's a beautiful chassis, and we're very, very excited about what it can do in the future. So I would just like to thank everybody for listening today and open the floor up for questions for whatever time we have left.